You know, sometimes we like to draw things symmetrical, but it's not always the case that it is symmetrical. The one I drew, though, has another problem. Does anybody else, does anybody like this structure, or does anybody particularly dislike this structure? I dislike it. Actually, I drew this, but I don't like it. I don't like this structure. I could draw one more because the double bond could go on this oxygen as well.
It would be the same thing as
Yeah. Yeah, as far as energy goes, it's the same thing. But as far as, we're looking at all the possible positions that we can move the electrons to. And so, yes, it's exactly the same as this. You know, you just flip it 180, but
you're not allowed to flip, so you just move the
yeah, you're not allowed to flip. So in probability terms, it's unique. It's a new one. And so it's like this. So, can anybody tell me why I dislike the first and the third structure? And I really like the second structure.
Does it have something to do with the double bond between carbon and oxygen and the hydrogen attached to it?
Yeah,
Do that?
it does. Because oxygen normally likes to form how many bonds? Oxygen normally likes to form 2 bonds. In this case, you know, this oxygen is not forming, you know, when I say it is forming 2 bonds, but this is a double.
The double one.
It's a single, so it's kind of like 3 bonds, right? If oxygen forms 3 bonds, then it cannot maintain its neutral formal charge. What's the charge on that oxygen? Got to be. It's like hydronium. You know, water is no problem. Water, oxygen forms 2 bonds, but hydronium is different. In hydronium, this is hydronium. Oxygen forms 3 bonds, but we have to do something, and that something is with the charge. Yeah, this is going to have a formal charge on the oxygen plus. Now, where does that plus come from? The plus comes from.
Because there's 5. Well, there's
Yeah.
5 electrons. It's 1 6.
Right, and so that's it. So if oxygen does indeed form 3 like this, then there's got to be it's got to be a positive. If that's a positive, where's the negative? Because the whole thing is neutral. Do you see the negative? Oxygen likes to form 2 bonds, but if it forms 3 bonds, it's going to be positive. If it forms 1 bond, it's going to be
That's 7 and 1 6.
right. And so this one. Now, does that look like a good, stable way to distribute electrons here?
So basically, you want to distribute the electrons to where there's a net formal charge of 0.
Yeah. Sometimes we can't help it because if there's a charge, this can never go to 0. There's a charge here.
Yeah.
This one, right. And so when we look at the formal charges in the second structure, they're all 0. And so this is quite a bit higher energy. This would be quite unstable. And so these we wouldn't consider resonance forms. But right now, we're just looking at things that are equal in energy or comparable. This is the same problem. And so there's only one structure here. It only makes sense to bond it, the double bond here, not here or here.
So when you draw a line like that between like carbon and oxygen, do you count that as 2 electrons when you're counting all the electrons? Because in total you're supposed to have 24 electrons in that entire carbonic acid model.
Yeah.
You count the valence electrons or whatever.
Yeah. Well, if we count the electrons here, there are 24 electrons in this structure.
That's what I'm saying, so like the lines, they count as 2 electrons?
Yeah, 2 electrons,
Okay.
each line. So this is a double line, so this counts as 4 electrons here.
Right.
In fact, some people do this with the lone pairs. Rather than drawing 2 dots like that, they'll just draw a line. So the line represents 2 electrons. That's quicker. So people like that. And so you'll see that often. All right, so there's only one structure for this. There's no resonance forms for this. You can only draw the double bond for this oxygen here. And So this oxygen we call a terminal oxygen. These oxygens we call bridging oxygens because they're bridging two atoms here. And so this is carbonic acid. Is carbonic acid stable? No, it's not stable. I mean, it decomposes, but it can be formed. You know, this is what it looks like. This decomposes into what? Carbonic acid decomposes into CO2 and water. But when we're drawing the Lewis structures, we don't care. You know, this is the Lewis structure of carbonic acid. Okay, I want you to do another one. We're going to complete the series. Why don't you do the Lewis structure for the carbonate ion? Carbonate ion is CO3. What's the charge on it? 2 minus. Now, with carbonic acid, are both hydrogens acidic, or is just one of these hydrogens acidic? Carbonic acid.
Technically both hydrogens, or
It's
is it-
both, yeah. And so we call this a diprotic acid. Both protons of both hydrogens are acidic. It's diprotic. And we can see it here in the structure. Hydrogens bonded to the oxygens. And we have nice symmetry there. Carbonate's also very nice and symmetric. Why don't you work on this one here? If you need some hints or some help getting started, let me know. Or just ask me how to get started. But you know, usually just follow these steps.